Okay, so let's take a minute before we actually start building circuits, which we'll do a lot this week. We'll do a lot of analysis of our circuits. Let's talk about a few important definitions for our unit in electricity. So the first really important definition that we're going to talk about is current. And current is basically the rate at which electrons flow through a circuit. Right? So if I connect this wire, then we can start to see these electrons actually like literally moving through the wires in our circuit, moving up through this light bulb and the filament, and then out through the other end and through the circuit back through the battery, and the cycle continues. So current is, again, the rate at which electrons flow through our circuit. And the most common unit for this is amperes, which we usually just show with an A. And the much more common way to say amperes is just amps. But I'll write out the whole name for completeness sake. So if we've got a current and some kind of flow of electrons and the speed or rate at which those electrons flow, there are also things that slow down the rate at which those electrons flow. So something like a light bulb slows this down slightly, slows down the flow of those electrons. Wires allow electrons to flow pretty much freely. There's very little impedance or opposition to that electron flow, but in something like a light bulb, that has more resistance than just our copper wires would. So what resistance is, again, is an opposition to electron flow. So something with a lot of resistance doesn't really allow electrons to flow through it. But something with very little resistance, like our wires, allows electrons to flow pretty freely through them. And so electrons are allowed to travel. But if we tried to use something like your hand or like a rubber pencil eraser or just a big rubber eraser, electricity and electrons are not really going to flow freely through that because they have too much resistance. Now, the most common unit for resistance is ohms, which is shown. This is the Greek letter omega, and that's just what they decided to, just to confuse anyone trying to learn physics. But it's just another Greek letter for us to learn. It's sort of like an O, but with these two little tails at the end. So we've got ohms as our unit for resistance, and if you click on the values here in the simulation, you'll see that we can control the resistance of this light bulb measured in ohms. So if we turn up the resistance, you can see that number of ohms increasing as well. Now, what actually causes a current to happen or these electrons to move throughout the circuit? And of course, you all know that that is our battery. Now, I'm going to talk for a little while about batteries, so bear with me for a second. And if you need to, make sure you go back and re-listen to or look back over our definitions of current and resistance. But let's start talking about what voltage is. So voltage is complicated. Essentially, it's a measure of differences in electrical potential. Now, what that means is if we have, and in a battery you literally have essentially this, I'm simplifying it certainly, but we sort of have two charged plates, right? And if I have one plate over here and one plate over here that's positively charged, there's some difference in electrical potential that would push something like an electron if we put an electron at the middle of these two plates, and the electron would be repelled by this plate, the negative plate, because opposites attract, so this negative charge is attracted to the positive plate and repelled by the same charges. So a negative charge will be pushed away by the similarly charged negative plate. And so this voltage is basically a difference of what the electron's potential would be right here to what it would be over here. Now, I'm going to go on a tangent for an analogy to what we've worked with gravity before, right? So, and I'll draw that in a different color here. What we've worked with before is if you were holding, let's say, a basketball, and you tossed that basketball up here. Here goes my really good art for a basketball. If you toss that basketball up here to some height, and then allowed that basketball to fall, there's a big difference in the potential energy that the basketball would have up at this height to the potential energy that the basketball would have down there. Right down here, depending on how we define our coordinate system, and we usually defined it so that the ground was like a 0 height, the basketball wouldn't have any potential energy at all here. But there's a change in energy that happens here, just like there would be a change in energy as this electron moves from this highly negative plate towards this positively charged plate. And what the voltage basically measures is sort of like a height, the electrical version of height. It is a measure of both the difference in the charges between these two plates. It's also a measure of the distance between these two plates. But our gravitational analog to voltage is that it's like the height, how high up I toss my basketball. And if I wanted to do something with the energy from this basketball, let's say that you wanted to, for whatever reason, we're assuming you have a younger sibling, a younger brother, sister, younger sibling, younger cousin, who is standing on one end of a seesaw. And you are, for whatever reason, trying to launch them. Maybe they've asked you to do this, launch them into a foam pit at Sky Zone. I don't know what you all want to do with this power that you have in knowing physics, but let's say that you dropped a 10-pound weight on this side of the seesaw, and you were trying to launch them into a foam pit, safely, of course, but still certainly dangerous no matter what. And what this voltage would be like, how high up you drop this 10-pound weight from, would determine how far that person would get launched, or how far your younger sibling or cousin would get launched into that foam pit. And depending on how far away that foam pit is, you would need more or less height. Of course, if you dropped this from higher up, it would launch your cousin or younger sibling farther. And so again, our analog to voltage, because I'm trying not to get on a seesaw tangent here, is that if we need more energy, or we needed our electrons to move even quicker through our circuit, if we wanted more current, then we could increase the voltage by increasing the number of charges on these two plates, or by decreasing the distance between these two plates. But those are the ways that we can control basically how high up we drop this ball from, or how we would give this electron more energy. And all this is to say that a voltage is a measure of a difference in electrical potential for our battery. So I'm sorry for the long-winded definition and description of what voltage is. It's a complicated topic. Hopefully this analogy to gravitational potential energy and the seesaw with your younger cousin or sibling helps. If not, I would be happy to answer questions and come up with different analogies possibly that are significantly clearer in the future. But those are our three most important definitions in electricity. That is current, or the rate of flow of electrons through a circuit; resistance, a measure of the impedance or obstruction to electron flow; and voltage, which is a difference in electrical potential.